All right, so now we're going to talk about atomic mass. We talked about mass number, which is protons plus neutrons. Atomic mass is different. Atomic mass is the average mass of atoms of a particular element, taking account the relative abundance of each isotope. So it's not an average in the purest sense of the word where you would add up all the mass numbers and then divide by how many there are. You have to take the percent abundance into account. And the unit for atomic mass will be atomic mass units, AMU. So this is your formula to calculate atomic mass. It looks very complicated. It's not, I promise. So it's the sum of fraction of isotope N times the mass of isotope N, and then sum of, right? So you would do that for each isotope and then add them up. Now, when I say fraction, what I mean is that's the percent of the isotope over 100 times the mass. So natural chlorine is 75.77% chlorine 35 and 24.23% chlorine 37. What is its atomic mass? So I'm going to do the fraction, so 75.77 over 100 times the mass of isotope 1, so 34.97, plus the fraction of isotope 2, 24.23 over 100, times the mass of isotope 2. If there was more isotopes, you would just keep going. If there was 5 of them, you'd do it 5 times, you know? So what I get for my first isotope is I get 26.49677. I'm going to underline that 9 to indicate that that would be my last significant figure, because in my percent and in my mass, I was given 4 significant figures. My second isotope, when I do that, I'm going to get 8.957. Dang it. 957.831. And again, I'm going to underline my fourth significant figure to indicate that that is where the rounding would take place. But don't round yet, because if you round too early, it's going to throw your entire answer off. So now I will add those together. I will get 35.454601. And since I added, now the rule changes to decimal places as opposed to total significant figures. So in my first isotope, 2 decimal places. In my other one, 3 decimal places. We always go with the fewest. So I'm going to round this to the second decimal place there. So 35.45. And then again, unit is atomic mass unit. Okay, and that's what you do for all of them. Like I said, if there's more isotopes, you do the exact same thing again. If you want to see one more example, here we have with copper. So the first isotope of copper, copper 63, is 69.17%, and it has a mass of 62.9291. The second isotope of copper, copper 65, has an abundance of 0.83. And a mass of 64.9278. So for my copper 63, I'm going to get 43.52806. 2 lines. 806. My mass had 1, 2, 3, 4, 5, 6. But my percent only had 4. So I'm going to go with 4. 1, 2, 3, 4. I'm going to underline my fourth significant digit. For my copper 65, I get 20.01724. Again, my percent had 4 significant digits. My mass had 6. So we go with the fewest. I'm going to underline 1, 2, 3, my fourth significant digit. I'm going to add those together, and I'm going to get 63.5453. Now the rule has changed, right, to addition, which is decimal places. So I'm going to look and see, okay, I got 2 decimal places there. I got 2 decimal places there. So I'm going to round this to 2 decimal places, 63.55. And again, unit is atomic mass unit. And you can always double check these with the atomic mass on the periodic table. Might be a little bit different because of rounding with percentages and that kind of stuff, but should be very, very, very close. All right, last thing here. So we have carbon has 2 naturally occurring isotopes, carbon-12, which has a 98.93% abundance, and carbon-13, which is a 1.07% abundance. Without doing any calculations, what mass is closest to the atomic mass of carbon? So again, you don't just add them up and divide. You have to take their percents into account, and carbon-12 is 98% of all the carbon in the world. Almost 99% of all the carbon in the world is carbon-12. So I would assume the carbon-13 isn't going to play a huge role in the atomic mass, and so I would say that its atomic mass would be closest to 12 AMU.